When it comes to collisions, there's several different types. You can have a variety of phenomena happening both before or after the collision, which can make collisions at times seem a little bit overwhelming. But I'm going to try and show you what I have found to be a fairly simple way to analyze these collisions. And it's nice in the sense that regardless of the type of collision you're speaking of, the analysis is the same. So just to kind of quickly show you a few brief examples, we have collisions where one object crashes into another object and then everything kind of stops moving. We have collisions where one object is moving, collides into a stationary object, and then after that collision, the object that was originally moving is now stationary, and the stationary object is now moving. So the velocity has kind of been transferred, so to say. We have collisions where one object is moving, one is stationary. After they collide, they stick together, kind of like if somebody was tackling another person. So one object was moving, one wasn't, and then they both moved as one unit afterwards. We have, furthermore, other examples such as two objects that are not moving at all, and then one object is moving and the other is not, or maybe one object's moving this way, the other object's moving the other way. So it's just kind of quickly to show you that there can be quite a variety of collisions. So collision is a very basic term, but as you can see by all of these examples, um, depending on what the object's doing before and after, that's going to affect how this collision or how these collisions are analyzed. Now, the purpose of this video is to basically look at two things. The first one is to understand the two classifications of collisions, despite the fact that I've showed you a few examples here. There's really only two classifications. And also start to look at the mathematics of collision analysis. This video is not going to go in full depth into the math behind it, but it's going to give you an introduction and show you the thought process you should begin to have when you analyze these collisions. So in order to better understand this classification of collisions, we have to realize that this whole classification system comes from two ideas. The ideal world, and that's kind of that world of the physics problems where it says ignore friction, ignore air resistance, things like that. In an ideal world, we have perfect energy transfers. So that just means no friction, no dissipated energy, etc. In an ideal world, if I dropped a bouncy ball, it would bounce back up to where, after it hit the ground, it would bounce back up to the original level that I dropped it from and would continue to do that perpetually. It would never run out of energy. Well, the real world is a little bit different. We have energy losses. We have frictional losses, dissipated energy such as sound and heat. So in the real world, if I drop that bouncy ball, every time it hits the ground, I get some sound. It technically produces a little bit of heat, and these are losses due to friction. And that's why when you drop a ball, depending on what the ball is made out of, it might return to 75% of its original height, and then the next bounce maybe 50%, then 25%. And essentially why every ball that you drop in the real world will bounce a few times, but then will ultimately come to rest. You have these energy losses in the real world. So the ideal world is really just used to help understand these concepts within physics, because the real world tends to have significantly more restrictions. It's incredibly more complex. So that's the reason why we look at these two classifications, the ideal world and the real world applications. But just to show you a quick example of each. So in both examples, I have a car that's traveling towards a wall, and it has kinetic energy of 1,000 joules. And in this case, there's no friction, anything like that. And in this case, we do have some friction. Now, after these two objects collide, well, in the ideal world with perfect energy transfers, this car hits the wall and bounces back. It rebounds, and 100% of that energy is maintained as kinetic energy. Since you didn't have any loss in energy here, that means you won't have any sound, heat, light, etc. So if you were not actually watching this collision head on, you would not even be aware that it even occurred. You wouldn't have any energy losses to sound, so you wouldn't hear anything. There'd be no heat produced, so you couldn't even possibly feel an increase in temperature or anything. You would literally see this thing silently bounce off the wall and go in the other direction. Complete maintaining of its energy. Now, in the real world situation, you started out with 1,000 joules, but when this car slams into this wall, you're going to have all sorts of noise. You're going to have some heat being produced, And all that heat and noise, that sound energy, has to come from somewhere. And that had to come from the kinetic energy. And that's why after these collisions in the real world, this object is usually not moving. It has no kinetic energy. It's lost all of that to other forms, dissipated energy, so to say. So again, an ideal example, nice for the physics world where you don't have to worry about all these energy losses. A lot more complicated, the real world scenario where you have all sorts of losses to heat, sound, the deformation of the car stores some energy, things like that. So the main difference, hopefully you realize, is that in one situation we have no energy losses, and in one case we have energy losses. And I put losses in quotes because obviously you're not losing it; you're just it's becoming another form, like dissipated energy. Now, these are those two main classifications, and the way we define these are what are known as elastic collisions and inelastic collisions. And I've just kind of described each of them to you, but an elastic collision is just a collision in which the object's kinetic energy is conserved. You don't lose any energy whatsoever to anything else. Whereas an inelastic collision is a collision in which the object's kinetic energy is not conserved. We have all sorts of losses, so to say, of this energy, this kinetic energy, to things like heat, sound, things along those lines, this dissipated energy. So those are the two main classifications, the elastic, meaning no energy loss, and the inelastic, meaning there is some kind of energy loss to some other form. You're not going to find any examples in the real world of an elastic collision. They do not exist. You cannot completely eliminate friction and things like that. Inelastic collisions are collisions that you see probably every day when two objects collide with one another. Just to get into the basics of the math behind these two types, the important takeaway is that momentum, just like energy, just like matter, is conserved. So in any collision, momentum will always be conserved. Whatever you start with will have to be whatever you end with. Now, the good news is when we analyzed energy, there were certain situations, such as in the presence of friction, so to say, where you could lose certain amounts of energy, and that's through this process of work, etc. So it could get a little bit interesting with energy. The nice part about the conservation of momentum, it doesn't matter if you have friction, don't have friction, if it's an elastic collision, an inelastic collision, it doesn't matter how complicated it gets. You will always have the same amount of momentum before as you had after. Does not matter about what else is present. As I said, friction, energy losses, doesn't matter, and momentum is always conserved. You take some objects in a lab and spend the rest of your life colliding them, you will find that momentum is always conserved, and no one has been able to prove otherwise. So, just to show how we can use this idea, this conservation of momentum, to analyze some situations. These are two different situations, so I apologize, it's kind of all crammed together, but let's look at this top line up here. Before, we have an object that has a momentum of 10 kilogram meter per second to the right, and a stationary object which has no momentum. So if I just add up my total momentum for this system for both objects, well, one has 10, the other has 0. So before any collision occurs, the total momentum in this system is 10 kilogram meters per second to the right. Afterwards, if this object stopped moving and its momentum is 0, well, this one would have to be 10 kilogram meters per second to the right, because when I add them up again afterwards, 0 plus 10 must give me 10 kilogram meters per second to the right. The total momentum before and after must be the same. So if this object collides with this one, and then that first object, which originally had 10, then is no longer moving, it's lost its momentum, that momentum must be conserved. It must have been transferred to the other object. Now, this also applies to situations where the momentum may be acting in opposite directions. So in this case, this object had a momentum of 8 kilogram meters per second to the right, and this object had a momentum of 3 kilogram meters per second to the left. So if I add up my total before, well, momentum is a vector, so I have 8 to the right, which would be positive. I have 3 to the left, which would be negative. So the total momentum in this system prior to the collision is 5 kilogram meters per second to the right. That is like the net momentum, so to say. Well, afterwards, if this object has its momentum reduced to 1 kilogram meters per second, but it's still traveling to the right, well, this one must be 4 kilogram meters per second, also to the right. How did I know that? Well, my total before was 5. My total afterwards must be 5. So if this one is 1, this can only be 4. Again, doesn't matter that these objects, one was moving, one was not moving. They were both moving towards one another. The key takeaway when analyzing these collisions, the total momentum you had before must be equal to the total momentum after in every single case. It doesn't matter what type of collision or whether energy losses are present or not. So just to show a real quick example again to explain how I got these numbers. Before, I have an object that has a momentum of 15 kilogram meter per second to the right, and I have an object that has 6 kilogram meters per second to the left. They're about to collide with one another. So if I look at my momentum before, I have 15 kilograms to the right, I have 6 kilograms to the left. So my total momentum before is positive 9 kilogram meters per second, or another way to say that is 9 kilogram meters per second to the right. Afterwards, I know that the first object has a momentum of 3 kilogram meters per second to the right, so it's been reduced. It lost 12. So what would the momentum of the second object be, and which direction would that be traveling in? Well, if I add up my total afterwards, I know that this is 3 to the right. I know this will probably have some momentum, but I don't know what it is, so I'll just call it lowercase p. Again, the key is whatever I had before must be equal to what I had afterwards. So if we take a look, I had 9 before. Afterwards, I had 3 plus whatever the momentum of the second object was. If I solve for that, I wind up with 6 kilogram meters per second, or 6 kilogram meters per second to the right. And when you think about it, it makes sense. This had 15 kilogram meters per second, and it dropped to 3. So the first object lost 12 kilogram meters per second of momentum. This object originally had negative 6, and if it gained the 12 that this one lost, well, negative 6 plus 12 will give me positive 6. So the big takeaway here is that momentum is always conserved. Whatever one object loses, the other object must gain. Whatever momentum I began with is the momentum I must have ended with. And don't forget that the two types of collisions we have are inelastic and elastic. Elastic simply meaning all my energy has been conserved and there are no energy losses. Inelastic, of course, therefore means that I did not conserve my energy and I lost it to forms like sound, heat, etc.